This is going to be really easy, I hope, because in just about every science class, the second chapter is always chemistry, and advanced placement biology is really no different. As I've taught chemistry here the past 3 years, I really, really hope you know this stuff because it's pretty basic. So I hope you find this very, very easy. So let's jump right into it. Your chapter starts with this really cool example of mercury as sort of chemistry being applied to something important in biology. They give it the name Mercury Rising. I think that's a movie reference or something, but basically mercury is a metal, a poisonous metal, liquid metal, by the way, that's released into the atmosphere by volcanoes. Also human activities like burning coal to generate electricity, burning trash, and even cremating dead people because mercury is part of the amalgam that a lot of dentists used to use to create dental fillings. And then when we cremate somebody and we burn all the way to ash, the mercury in their teeth is released into the atmosphere. So the cool thing about mercury is that it doesn't really get into our bodies as mercury. As a metal, it's pretty much going to be not in our bodies. But one bad thing about mercury is once we blast it up into the atmosphere, it goes a long ways. It settles to the Earth's surface or our oceans. And the oceans, little microbes convert it into methylmercury. Methyl is connecting CH3, a methyl group, if you recall from organic chemistry, onto that mercury. And this is really bad because mercury itself is not really going to stick in you and stay there forever. Methylmercury is fat soluble, which means it gets in the tissues of little tiny animals, which isn't a big deal because the levels are very small. But as you'll recall from general biology, perhaps, there's something called biomagnification or bioaccumulation, which means that a little fish eats lots of small algae, and a little fish gets a little bit of mercury in him. And then a bigger fish eats a whole bunch of little fish, so a bigger fish gets a lot of mercury in him. And then the really, really big fish that eats him gets a lot of mercury in him. And then we catch him, and we cut him up for sushi, and we eat him, and then we get a lot of mercury in us. So you kind of get the idea there. Once mercury enters the body, it's going to damage your nervous system, your brain, your kidneys, other organs. It's pretty toxic stuff. And every human on the planet has detectable amounts of mercury. If you're not breathing it in, you're getting it in your fish. And that's just something we're going to have to live with. So good connection for chemistry and biology. So here's the example of our coal plant combusting coal to make probably electricity, and all of the smog coming off of that coal plant has mercury in it. Here's a picture of mercury. It's a liquid. It used to be used in thermometers. We've changed to a red dyed alcohol because if you break a thermometer full of mercury, it's toxic. And then this is a tuna. Tuna fish is pretty much top of the food chain, and he's going to have the most mercury in him because he's at the tippy top. So if you get the option between eating a bluegill and eating that 20-pound trophy pike, opt for eating the bluegill and you'll have less mercury in you because the pike has bioaccumulated it. So chemistry starts with atoms. The behavior of elements, which make up all living things, starts with structures of atoms. The number of protons that are in the atomic nucleus defines the element. The number of neutrons defines the isotope. We're going to go over some terms like atomic number. That's the number of protons in an atom. And then atomic mass is the number of protons and neutrons. Do you recall why we don't include electrons in atomic mass? Hopefully you remember that electrons' mass are so super small that they're negligible as far as changing the mass of an atom. So, pardon me, atoms are building blocks of all substances. We make atoms up of electrons, protons, and neutrons. Our protons and neutrons are in the atomic nucleus. Electrons are flying around on the outside of that nucleus in a cloud. The charge is the electrical property of atoms. Atoms can have a negative charge or a positive charge, and that can attract or repel other atoms or other subatomic particles. So, electrons are negative. They move around our nucleus. The nucleus has positively charged protons and neutral neutrons. Neutrons don't affect our charge, but they do affect our mass, so they are still important. Atoms differ in their numbers, their atomic numbers, the number of protons. This is what we use for our periodic table. Hydrogen's number 1, helium's number 2. You number these off by the number of protons. The elements consist only of atoms with the same atomic number, and our mass number is what it weighs. Think mass like a triple beam balance you use to get the mass. The mass is the number of protons and neutrons because they're the only thing that weighs anything. We also use the mass number to identify isotopes because if it's heavier than it should be, perhaps we have some extra neutrons in there. And if we know it's carbon, but it's lighter than it should be, maybe we've lost some neutrons. So that's an important thing to understand. Here's an example of your very, very basic diagram. You got a proton in the middle, you got a neutron in the middle, there in a nucleus, out here are electrons surrounding it in a cloud or a shell. So we arrange our atoms on the periodic table. You're most certainly familiar with this at this point in your life. We arrange them based on their atomic numbers, and the reason we repeat and have a table that continues to go back to a first column is because they have similar chemical properties. And you'll recall that that's because of the number of valence electrons, that they'll bond with certain things or they won't bond with others, or they'll react with metals, things like that. That has to do with the number of valence electrons they have. Dmitry Mendeleev was the one who came up with the periodic table that we use today. And hopefully you recall from chemistry that he was so confident in his design that he left blanks in his table for 3 elements that he thought should exist based on the trends he was seeing. He just didn't think we had discovered them at the time, and he was correct. Here's our everyday periodic table. So hydrogen, 1 proton, helium, 2 protons, cobalt, 27 protons. As you move down, you're going to get quite a bit heavier. We name all of these, alkali metals, alkali earth metals, transition metals, things of that nature that you'll recall from general chemistry. So isotopes are an interesting thing when we start talking about biology, because what we get is different forms of the same element with different numbers of neutrons. So it's still carbon, but it has a different number of neutrons. Maybe it's a carbon-14 to a carbon-12 or something like that. Some of these guys are radioactive. We call them radioisotopes, and these are really cool because we can use them in research and medical applications, and you really don't have to go far to have this done. They can do this actually right in Rapid City. It's kind of a neat deal. They give you a radioisotope in like an egg or something, and you eat this radioactive egg, and they take pictures of your stomach or your intestines, and they can see a glowing picture. Basically, it's glowing inside of you, and they can detect that with all sorts of machines, and it's really cool. So they can see how your intestines are doing, kidneys, heart, all sorts of stuff they can take pictures of nowadays, and it's really pretty amazing. So this is radioisotopes. Henry Becquerel discovered these in uranium in the late 1800s, and it's radioactive decay. They're emitting these subatomic particles of energy when that nucleus breaks down. And so it does change one element into another at a constant rate. And so here we have carbon-14. We have a nucleus of carbon-14. It has 6 protons. It has 8 neutrons. And then as it's becoming radioactive, you can see now we have 7 protons. So we've gained 1. And 7 neutrons, so we've lost a neutron. And so we emit energy when we make that change, and if this occurs at a steady rate, it allows us to use it as sort of a clock, which is a nice deal as well. So a tracer, this is the one I had mentioned earlier, a molecule with a detectable substance attached. How we take a picture of, the inside of a person without using an X-ray, or how we track carbon in carbon dioxide through a photosynthetic leaf, we use a tracer. And so here they took carbon dioxide, they tagged it with carbon-14, and we tracked carbon through photosynthesis, and we use radioactive tracers in medical scans as well. So here's a picture of a really cool tracer they use, and basically the red is having more of this molecule, and the light colors are having less, and people who have less are a little less healthy and a little more aggressive, and all these other kind of trends they talk about in your book, and they compare the levels of this molecule in the non-smoker and the smoker, and what this photograph has shown. So there's all sorts of neat little applications to things like this. So our take-home message for the first section. All the matter, a table, a desk, you, a tree, a rock, it all consists of atoms. Atoms are teeny tiny particles that consist of electrons that move around a nucleus, and that nucleus contains protons and neutrons. An element is what we would call a pure substance. It consists only of atoms with the same number of protons, and isotopes have varying numbers of neutrons. Unstable nuclei of radioisotopes disintegrate spontaneously or decay at a predictable rate to form predictable products. And as we talk about the age of the Earth and evolution and the creation of the Earth and some big topics that are difficult kind of to understand, we're going to talk more about these radioisotopes used as a dating method for how long a tree has been dead, or perhaps how long a rock has been around. And so it's kind of a useful thing there as well. So that's the first section. I hope you find that pretty easy. Let's jump to the next one. Atoms. Why we focus so much on electrons when we talk about chemistry? It's because atoms can gain electrons or donate electrons or share electrons, and whether an atom interacts with other atoms depends on how many electrons it has. Just quick review. For most atoms to be happy with the number of electrons they have, how many should they have? Hopefully you said 8. We called that the octet rule in chemistry. 8 atoms, or 8 electrons rather, is a happy atom. 8 electrons in its valence shell is the general rule. There are exceptions to that, but when you think of guys like helium with 2 or neon with 8, they don't really want to bond with anybody because they're about as stable as you can possibly get. So electrons are going to move around these nuclei. They exist in particular orbitals. 1 through 7 are your primary or principal energy levels we talked about in chemistry. Each orbital holds 2 electrons. Each orbital corresponds to an energy level, and an electron can move only if there's a vacancy. And so sometimes we get atoms that have a vacancy, and we call those a free radical. And that is an atom that has an unpaired electron. So think of that as an unfilled or partially filled shell. And partially filled shells are a bad deal. So if you have 2 electrons, I just love this picture, 2 electrons, it's like 2 old people on this tiny balcony. There's no vacancy here. There's a shell, there's 2 electrons in the shell, that's an electron pair, and they are stable. This electron shell, or teeny tiny balcony, has a vacancy. There's 1 person on that teeny tiny balcony, and there's a vacancy. Now the atom is going to want to fill that vacancy. The reason that free radicals are so bad for biological organisms is she wants to fill that vacancy, and they will rip electrons from neighboring atoms to fill that vacancy, and that can do a lot of harm to biological organisms. So you might have heard these terms like antioxidants, like, oh, you should drink whatever tea because it's packed with antioxidants. Antioxidants are so popular because they're good at getting rid of these free radicals, because those are kind of a bad deal to have cruising around your body. So there's a good picture for electrons, I guess. So the shell model of electron orbital diagrams show these electron vacancies, and we fill them from the inside out. We have a first shell, it's 1 orbital that can hold 2 electrons. The second shell holds 4 orbitals, which holds 8 electrons, and the third shell holds 4 orbitals, which holds 8 more electrons. You might recall from chemistry, 1s2, 2s2, 2p6, that sort of stuff. That's where we're getting our 2s and 8s from. Atoms that have vacancies want to give up electrons, get electrons, or share electrons to try to fill that vacancy. So here's a diagram for how we increase our numbers of protons and electrons. So diagram A here, the first one, the first shell corresponds to the first energy level. It holds 2 electrons. So hydrogen has 1 proton, so it has 1 electron and 1 vacancy. Hydrogen's bonded to a lot of stuff, water and all sorts of things. If you look at helium, it has 2 protons and 2 electrons. So it has filled its first energy level. and there's no vacancies. So if we move up the periodic table a little bit, we have a second shell. The second shell can hold up to 8. And so if carbon has 6 protons, its first shell is full, that gets us to 2. Second shell has 4, and it has 4 vacancies. So you're going to find carbon bonding to a lot of things. Oxygen has 8 protons, and so we get 2 electrons, and then we get 6 more to get 8 electrons, because we generally want to have the same number of electrons as protons, but it still gives us 2 vacancies. So understanding chemistry helps you understand, why can carbon form 4 bonds and oxygen only form 2? Because of the number of valence electrons in its outermost shell. Neon is at number 10, so neon has 2 on its innermost level, 8 on the outer, and it is completely stable as it can be. So if we move to a third shell, our third energy level, we can hold 8 again. Sodium atom, we're looking at 11 protons, so we're going to want to have 11 electrons. We're at 2, we're at 8, that makes 10, and we get 1. This is the free radical picture we painted before. This is that one lonely lady on her teeny tiny deck, and sodium wants badly to bond with somebody. So you're going to find it as sodium chloride. If you have just a brick of sodium, it'll bond with the water in the air and just blow up or light on fire because it's that reactive. So important, absolutely. The sodium ion is very important in biological systems, but as a free radical, it's very dangerous as well. So here's chlorine with 17. So we've got our 2, we've got 8 for 10, and we've got 7 in the outermost shell. And so here you can see why sodium and chlorine bond. If they share, we get 2 for sodium, 8 for chlorine, and they're stable. And then argon, having the complete octet in the outermost level, makes it very stable as well. So, terms that you'll know: atoms and ions. If an atom has a positive or negative charge due to a loss or gain of electron, that's what makes it an ion. Just this, an atom with a charge. That's all it is. If it's positive, it's a cation. If it's negative, it's an anion. And then electronegativity is a measure of its ability to pull electrons away from another atom. Think of it as how greedy an atom is for somebody else's electrons. Your heavy hitters in electronegativity are going to be fluorine, oxygen, those kind of guys. Maybe nitrogen, chlorine. Think the top right. You kind of got the idea. So here's sodium. His option is to either gain 7 electrons or lose 1. A lot of times he's going to choose to just lose 1 and become, a sodium plus 1. And that's going to make him really stable. Here his charge is 0, but he's not very stable. If he becomes the ion, he's a lot more stable with the charge of a plus 1. Here chlorine's going to gain that electron. Perhaps that sodium lost. And chlorine had 7 in its outermost and was not very stable. But if we give it that -1 charge because we gained a negatively charged electron, we become a lot more stable. And so why are atoms gaining, losing electrons, sharing? So they can become more stable. So what's our take-home message for the third section? An atom's electrons are the reason it behaves the way it behaves. We represent these electrons in shells at different energy levels. And if our outermost shell is not full, we call that a vacancy. Atoms with our vacancies are going to tend to interact with other atoms, and atoms with no vacancies are stable, so they don't really interact with anybody. So that is where we'll stop for now. Thank you.